In this session, let's try to understand another most powerful machine learning algorithm called as support vector machine. So just like neural networks, you find that support vector machines are also very complex to understand. So the mathematical models behind the support vector machines are also very complicated. But at the same time, because of the various technologies like R, which have already built in the various attributes associated with support vector machine, as a business user, I can very well use those support vector machines for doing my prediction purposes. So I can train my model, I can train the machine with this support vector machines algorithm on the training data, and based on whatever the learning that the machine has been able to do, I can use that learning to do the prediction on the testing data before I roll it out to the production world. So as a part of this session, just like in neural networks, I won't be getting into the detailed mathematics associated with the support vector machines, but some basic terminologies, some basic conceptual aspects that are associated with the SVMs, I'm going to cover them. So initially we'll talk about what are support vector machines, how do you differentiate between support vector machines and the various other machine learning algorithms we have seen till date. So here we use a terminology called hyperplane. So how is this classification of the data occurring with the help of hyperplanes? Right, I can use this both for classification purposes as well as for numerical prediction purpose. So we can see how is this grouping occurring with respect to hyperplane. So how do I really identify what is hyperplane first of all, and how do I really identify the maximum margin hyperplane for the data which is linearly separable, or in case of non-linearly separable kind of a data? How do I differentiate in terms of finding out the hyperplane? And then we are looking at what do we really mean by kernels. In case of support vector machines, we talk about kernels especially for non-linear spaces. So if the data is, if the relationships between the variables are non-linear, we talk about converting them into linear using what are called as kernels. So let's try to understand what those kernels are all about. And then we talk about different types of kernel functions that are there, specifying what are the goodness, what are the advantages and disadvantages that are associated with support vector machines. So once we have a good understanding of the basic theoretical aspect behind the support vector machines, we can very well continue the same prediction example that we have done, and we can go ahead in terms of predicting with the help of support vector machines, and finally do the goodness of fit of the model by finding out the R squared on the test data. So conceptually, when we are talking about support vector machines, we are clearly defining a surface. We are defining a surface. So we are talking about different points. So let's say these are some set of points, these are some set of points. We are defining a boundary between various set of points. Different ways in which I can define the boundary. I am defining a boundary between various points of data according to the feature value. So we are having the various data plotted, and I am trying to segregate the different kinds of data by drawing boundaries across the various elements. So the major goal of support vector machine is create a kind of a flat boundary. So the flat boundary could be a two-dimensional boundary, which is simply a line, or it could be a three-dimensional boundary or n-dimensional boundary, which is a plane. So that kind of a boundary that we are drawing or creating is called as a hyperplane. So the intention is whatever the partitioning that is happening on the data, so the values are more or less uniform on either side of the partition. This is more and more we are talking about the categorical data. Of course, the same thing will be applicable even for numerical data also, but when we are splitting or when we are drawing the boundaries, we want that those values that are falling within the boundary, they need to be more or less homogeneous, whereas the others which are falling on the other side of the boundary, they should be very much away from this set of values. So there is some kind of a combination of KNN algorithm, which is primarily for the classification purpose, and also a regression algorithm, which is primarily for numerical prediction purpose. So even if the relationships are very complex, even if I have to do a classification or if I have to do a numerical prediction, for any kind of aspects, I can very well use the support vector machine. So there are so many softwares. See, theoretically, understanding them could be very complex, but because of the presence of various softwares, because of the different implementation of the various techniques in various software libraries like R, even though the math is difficult, I can very well understand the whole process. I can use them for the prediction or for creating a model with the training data, evaluate the goodness of fit of the model, and if the model deemed to be more appropriate, I can very well validate the model on the testing data, and if the accuracy of the model looks much better, I can very well roll it out even onto the production data as well. So that's where the SVMs can quite comfortably be used, even if my objective for any kind of a supervisory learning process, even if my objective is classification of the data or even a numerical prediction, in both the cases I can very well use support vector machines just like the way I have used neural networks as well. But when we are talking about binary classification, probably I get the best out of the support vector machines, where I am able to divide that whole data into two groups. So the kind of a plane that I am using for dividing the data, so the understanding will become more and more comfortable when we are using the objective of binary classification. Now, this is how the binary classification typically works, right? It's a kind of a line that I am drawing between the variables, or if I have multiple features, instead of a line, I am drawing a plane. So SVM is actually using a linear boundary. It could be in a two-dimensional, if it is a line, in the multi-dimensional, it's a plane. So in general, we are calling it as a hyperplane. So to partition the data into groups, so if it is a plane, if it is multi-dimensional, then we look at it as a plane, otherwise it's a simple line that is doing the bifurcation between the groups. So they are all linearly separable. So I can very well separate the groups with a linear line or a simple plane. But I can very well extend this mechanism even if the groups are not linearly separable, even if they are non-linearly separable. We say we introduce a scenario called kernels. So because of this kernels, even if the data is not linearly separable, we can use an appropriate kernel to transform the data such that it becomes linearly separable, and we can very well go ahead with the model building process. Coming to the SVM algorithm, the main objective is I should be able to, when I am executing an SVM algorithm,